Welcome to shadow trajectories for repeated eigenvalue, eigenspace dimension 1. So we're going to focus on 2 by 2 case. So focusing on the 2 by 2 case. If the system y prime equals ay has repeated eigenvalue lambda, lambda 1 equaling lambda 2, and eigenspace of dimension 1. Then the general solution takes the form y equals c1 times psi1 e to the lambda 1t plus c2 times, in parentheses, psi1 t plus eta 1, where psi1 and eta 1 are vectors, all multiplying e to the lambda 1t. And this is where psi1 is an eigenvector and A minus lambda times the identity matrix times eta 1 is equal to psi1. So we are focusing on this specific case where we have sort of our two fundamental set of solutions. One is just a vector times e to the lambda t, and one is a vector times t plus another vector times e to the lambda t. So the question is, what does this mean for shadow trajectories? So let's just first off focus on the e to the lambda t component, and then we'll focus on the other part. So note if lambda 1 is greater than 0, then our solutions will start at the origin and head away, right? So the solutions will go to the origin as time goes backwards. So we'll essentially will come from the origin and head outwards. On the other hand, if lambda 1 is less than 0, then the solutions will start far out and head towards the origin. So the solutions will head towards the origin. We'll focus on those two cases first. In the case where lambda equals 0, we'll essentially be looking at lines, right? So if lambda 1 equals 0, then we're looking at y is equal to c1 times psi1 plus c2 times psi1 times t plus eta 1. This c2 multiplying psi1 t plus eta 1. And this will just take the form of a line. and this line will run parallel to Xi1. All right, if we focus on the part multiplying e to the lambda t, note that the C1 Xi1 plus C2 times Xi1 t plus eta 1 component, this piece here will be this will be negative in the direction of Xi1, or opposite of Xi1 for basically large negatives. So this will look like, for C2 greater than 0, this will look like a large scaling of negative Xi1, right? So as t goes to negative infinity, the Xi1 will sort of overpower. And it will be negative because it's being multiplied by t. As t goes to positive infinity, Xi1, oops, sorry about that. As t goes to positive infinity, again, Xi1 will overpower the eta. And so it'll move just in the direction of Xi1. So for negative t's, we'll kind of be in the opposite direction from Xi1. For positive t's, will be in the same direction as Xi1. For C2 less than 0, the opposite will be true. So now we're going to put these two pieces of information together. So I need to give myself just a little more space. Again, putting these together, if we look at the case where lambda 1 is lambda 2 and they're both positive, we have our representative Xi1, and then we also have our representative eta 1. Whatever that vector is. So we'll have one solution, which will just run right along Xi1. This is going to be the case where C2 is equal to 0. And we're just looking at a scaling of Xi1, and it will, the scaling increases as time passes. So we're heading out from the origin. And for C2 greater than 0, we will be pulled slightly in the direction of eta, but we're starting off as we, that C1 Xi1 plus C2 Xi1 t plus eta 1, we will start off at the negative infinity side, looking like negative Xi1. So we will start off looking like negative Xi1 with a small scaling coming from the origin. And then as time passes, it will start to look like positive psi1. So we essentially loop away, sort of curl away from the solution, starting off going in the negative direction and then curling our way around to heading in the positive direction along psi1, kind of almost running parallel. Oops. On the other hand, if we look at the side where C2 is less than 0, for negative values of t, we're actually going to start off going in the direction of a positive psi1 for large negative values of t. We're going to start off in the direction of positive psi1 with a tiny scaling, and then we'll curl our way around and head back the opposite direction in the direction of negative psi1, sort of curling away. And this is on the side that does not contain eta 1. So we kind of get sort of things that look somewhat like an S curve. Keeping in mind that the solution only takes one of those curves of the S, since as time goes towards negative infinity, it kind of gets sucked into the origin. Taking another one, let's look at with lambda 1 equaling lambda 2 less than 0. So in this case, again, we start off with the same picture. We have our representative psi1 and our representative eta 1. For C2 equaling 0, we just are directly along psi1. This time around, as time passes, we head towards the origin. So we should have a line through the origin following along the direction of psi1 and heading towards the origin. Now, if we look at C2 positive, then we will be on the side where we have our eta. As time goes to positive infinity, the component, the C2 times psi1 t plus eta 1 component looks like it goes in the direction of psi1. So, and as t heads towards positive infinity, we head towards the origin. So this time around, we'll actually start off looking like we're in the as we're near the origin, we will look like we're in the direction of psi1. So and then as time passes, it will sort of curve around and ultimately head running parallel to psi1, but looking like it's going in the opposite direction. So essentially, as time passes, we start off far from the origin, we're sucking into the origin. And far from the origin, we're on the opposite, running parallel to our line through psi1 in the opposite direction. Close to the origin, we're running right along psi1. And again, being sucked into the origin. Then we have the opposite of the S curve on the other side. So for C2 less than 0, for large values of t, when we're close to the origin in this case, we will look like negative psi1. For large negative values of t, we will look like positive psi1. Again, that's when we're far from the origin. It will look like we're on the positive side. And then for psi1, when we're close to the origin, it will look like we're going in the negative direction. So again, we get this kind of S curve appearance, this time sucking into the origin. And again, on the side, when we have lambda greater than 0, on the side of, if we draw the line for psi1, and then we look at the side containing eta, we start off heading away from psi1 and then curve around. In the case where lambda is less than 0, if we look on the side that has eta, we start off along psi1 and curve our way out as you're sketching it. Of course, as time passes, we're actually heading into the origin. In the case where λ1 equals λ2 equals 0, we have our two vectors. We have our psi1 representative vector and eta1 representative vector. When C2 is equal to 0, we are just along this line. Along the line through the origin in the direction of psi1. And we're not moving in any direction. For C2 greater than 0, essentially we're just going to have a bunch of parallel lines running parallel to psi1. And in this case, they are going to head in the direction of psi1 as time passes. Then for C2 less than 0, the side not containing eta, we will once again have parallel lines, this time heading in the opposite direction of psi. So these are the various cases that we can wind up with when we have that repeated eigenvalue with eigenspace of dimension 1. Last up, let's go ahead and do an example. Oh, there we go. This is from the previous video. So from the previous video, we looked at the system y prime equals first row 1, 4, second row -1, 5, and multiplying y. And we found the general solution. To be y is equal to C1 times the vector 2, 1 times e to the 3t plus C2 times the vector 2, 1 times t plus the vector -1, 0, all multiplying e to the 3t. So again, we had psi was equal to the vector 2, 1. We have eta is equal to the vector -1, 0. And we had lambda is equal to 3, which is positive. I'm just going to verify quickly that I did record that correctly. That is what we had. So in this case, when we sketch, we know that we're heading outwards. If we draw our sketch, psi1 is the vector 2, 1. So we'll draw the vector 2, 1. This is our psi. Eta is the vector -1, 0. So we draw that vector -1, 0. This is our eta. So we know that we have solutions heading outwards along the line through the origin with direction psi. Then this is our C2 equaling 0 line. C2 greater than 0, we're going to look at the side that has eta on it. So in this case, we're looking above our line. We start off heading in the opposite direction. Again, we're looking at the case with lambda is positive. So we start off from the origin opposite direction of psi, work our way out and curve back around to run parallel to psi. I apologize, I need to update my screen. So again, on the above the line, we kind of start off going in that opposite direction, heading into the third quadrant, and then curve our way back around. And then on the C2 less than 0 side, we are this time under our line alongside. We're going to start off heading into the first quadrant, running alongside, and then curve the way around and head back to run more in the direction of negative psi. So again, we're heading out from the origin along all of these paths. So this is how we can do curve sketching in the case where we have repeated eigenvalue and eigenspace of dimension 1.